Okay, so today should be a pretty quick video, but it's going to be a decent length lesson. It's going to be on relative motion, just like it was last class, but I want you guys to get a little bit of independent practice today. So here's today's plan. So like I just said, mostly a practice day today. We're going to do a couple of examples on two-dimensional vectors and relative motion, just like what we did last class. I want you to be trying these couple questions either on your own or with a partner. I don't really mind if you work with a partner here. Matter of fact, it might be a good thing. We do need, to some extent, some independent practice rather than you listen to me blab on. There's going to be lots of practice time today to finish off those whole bundle of worksheets I've given you in the last couple of days that kind of overwhelmed you, I think. I know it says exit slip in the last 15 minutes. We aren't actually going to do that, so don't worry about that. I just didn't remove that from the slides. Here we go. So first question, and I'm not having these printed off for you guys, so you're going to want to copy this down when you can. Elian decides to go hang gliding. He's pointed west, traveling at a constant 15.5 meters per second west, but there's a wind from the north blowing at 5.00 meters per second south. The question's asking, what is his velocity? Remember, velocity is a vector relative to the ground. Pause the video here, jot this question down, give it a try, and I'll go over it in just a second. Okay, I'll go over this now. So again, it says he's pointed west, traveling at 15.5 meters per second west. So west, of course, is this way. So he's pointed this way, and that's going to be 15.5 meters per second. Now there's a wind from the north pushing down, though, at 5.00 meters per second to the south. Now that's going to cause, especially when he's hang gliding, that's going to cause him to actually change course a bit. So even though he's pointed to the west and traveling in an X direction to the west, the wind from the north is going to push him a little bit off course, about like this far, we'll say, down to the south, 5.00 meters per second. And just remember, even though these are like speeds or velocities, I guess, you can still use them when you're using vector diagrams, right? So with velocities, as long as they're just going at the same time, it can still work just fine. So relative to the ground, that's gonna be this diagonal measurement right here. So it's this measurement from the starting point to the ending point, because he's actually, relative to the ground, he's actually going to have a diagonal motion to him here. So the question is saying, what is his velocity relative to the ground? I kind of hinted before you started the question, we need not just only the magnitude, but we'll also need the direction because it is a vector. The magnitude is probably the easier part here. Notice this is just a right triangle. To find this hypotenuse right here, you just got to use Pythagoras. So you'll just say 15.5 squared plus 5 squared equals, we'll call that c squared. So 15.5 squared plus 5 squared gives me 265.25, and that equals c squared. We got to get that square rooted though, so square root both sides of that equation. Square root this, and I got c equals, how many sig digs do we need? Oh, 3 sig digs. So 3 sig digs, it's going to be 16.3 meters per second. So that's all well and good for a magnitude. So if this question was asking what is his speed relative to the ground, we'd be done right there. That's what we would have. But because it's asking for a velocity, we do need to have a direction. And remember, the way that we communicate this direction is often a little bit weird, right? Notice he's going west and then he's going south. So this angle right here, I'll call it theta, that angle right there is going to be south of west. Remember, it is kind of backwards, right? So he's going west and then south, so it'll be south of west. It's south of west. I know I really drill that in, but every year there's people who have trouble with that, which is fine. Anyway, now that we know it's south of west, we need to also figure out what the actual, angle measurement is there. This is just going to be a matter of using a little bit of trigonometry. So notice we know 5 meters per second, that's our opposite side, at least compared to theta. And 15.5 is our adjacent side compared to theta. Opposite and adjacent from SOHCAHTOA, opposite and adjacent matches up with tan, because tan is opposite over adjacent. So we can say, let's do it over here, tan of theta, for whatever theta is the opposite side, which is 5, divided by the adjacent side, which is 15.5. To get theta all by itself, you have to use inverse tan. So we're going to use inverse tan on both sides. It's just going to knock out tan over here. And then we have to use inverse tan of this entire chunk right there. So you might as well put it into inverse tan as a fraction, just straight up like that. Remember, make sure you're in degree mode in your calculator. I don't think there's any reason for that to have changed, but it's always worth noting. So I'm going to take inverse tan of 5 over 15.5. And once again, to 3 sig digs, we've got theta equals 17.9 degrees. Now we have to wrap this up. Having our answers separate like this doesn't do anything. We have to communicate it as a solid velocity, like an actual vector answer. So for my final answer, I'm going to say 16.3 meters per second. And then in square brackets for our direction here, 17.9 degrees. And remember, he went west and then south. So it would be south of west. And that right there, I'll put a big box around it. That is our final answer for that question. So all in all, hopefully that wasn't too terribly bad. There's a lot of really, interesting math things that come around here. We had to use Pythagoras, and then we also had to use sine, cosine, tan. Well, just tan, I guess, in this case, but you had to know about them. So trigonometry comes back pretty rough in this. So make sure you know how to deal with that. And if you don't, make sure you're working with someone who does, so that they can hopefully point you on the right track, or at very least ask me when you get back to class, or when I get back to class, whenever that will be, hopefully very soon. Anyway, tough example, just a heads up. This one's a tougher one. It's going to take a little while. Eric is playing football. He ran 15.0 meters at 50 degrees north of east, dodged another player, and then ran 35.0 meters, 10 degrees south of east. Find his final displacement. Remember, once again, just like velocity, displacement is a vector, so we need a magnitude and a direction. Pause the video here, jot the question down, give it a try either on your own or in pairs, and I'll go over it in a second. All right, so I'll go over this now. First things first, hopefully y'all did this, draw a diagram, right? It makes it so much easier if you just draw a diagram, and also try to draw it like properly, like to scale and everything. So 15.0 meters at 50 degrees north of east. North of east means we're going to go east and then north. So I'll start right over here. We'll say we're going to go east and then we're going to go north. Now 50 degrees is like a pretty reasonable angle there. So I'd say that's maybe a little higher. There we go. That's probably about 50 degrees. So we'll say that's your 15 meters. Make sure I label that 15 meters, and the angle was 50 degrees, and that is north of east. And then from that point, he ran 35 meters, 10 degrees south of east. So south of east means you go east first and then south. And 35 meters is more than double what we just did here. So I'm actually going to go quite a ways here. So I'm going to go all the way, I'm going to say like all the way over there at least. And then 10 degrees south of that, that's not very far south of it. That's maybe about there. And then I'll just connect that. Now, here's what's kind of an unknown, right? I'm betting that in our final answer here, I'll just do it in a different color. I'm betting in our final answer, our total X and our total Y will look something like this. So in other words, what I'm trying to say is I'm willing to bet in this case that our final Y direction will end up being a little bit to the north, because at that 50 degrees at 15 meters, I bet that took him further north than just 10 degrees, which isn't very far off this for 35 meters, but I could be wrong. There is a serious possibility that my diagram is not accurate, but we'll have to do some calculations just to make sure. Remember, the calculations that I'm alluding to here are finding all of your possible X and Y components. So we need to find, I'll call this X1, that's just this part of the first triangle we made, and this is Y1. And then I'll also need to find X2 and Y2. And I just realized I totally forgot to write in there that 10 degrees. That's really important. Right over here, that was 10 degrees. And also this is 35.0 meters, my mistake. Anyway, let's find all of our X and Y components here. I'll start with that very first triangle. I'll just do it over here to save some room. I'm going to focus on finding X1 first. Notice in this right triangle that forms right here, X1 would be your adjacent side, and 15 is your hypotenuse. Well, from SOHCAHTOA, there we go. From SOHCAHTOA, adjacent hypotenuse, that's going to be cosine, right? So for X1, we can say that cosine 50 degrees equals X1, that's your adjacent, over your hypotenuse, which is 15. Hopefully you remember from this, to find X1, we just need to multiply by 15 on both sides. I'm not going to show all that work, nor do you. So 15 times cosine 50, oops, my calculator's kind of got a mind of its own here. Hold on, 15 times cosine 50, there we go. Remember, this is not a final answer, so try to keep as many decimals as you feel comfortable doing. I'm going to say that this is 9.6418. That's probably as far as I really need to go. I don't think I need to go further than that. Now let's find y1. Y1 is the opposite side in that triangle. Opposite and hypotenuse, that's going to be sine. So sine 50 equals opposite, which is y1 over hypotenuse, which is 15. Multiply by 15 on both sides, so 15 times sine 50. That's going to give me y1 equals 11.4907, we'll say. I'll just round that to 7. All right, so that's good for the first triangle. Excuse me. So now we need to find x2 and y2. Let's just divide this over so we don't lose track of everything. X2 on this triangle, I want you to notice that's your adjacent side this time, and y2 is your opposite side. So this time we have adjacent and hypotenuse. Adjacent hypotenuse is going to be cosine, so we can say cosine 10 equals, what would that be? Okay, that would be x2 over 35, multiplied by 35 on both sides, and you have x2. So let's see, 35 times cosine 10, there we go, that's going to be 34.4683, 4683, and that'll be all good. Now, if you kind of noticed, I kind of like stopped and paused there for a second. It's because something just went through my mind. I kind of think when we list all these, we should probably list not only the number, but also, of course, our units and our direction. My mistake, guys. So in this case, for the 34.4683, that'll be meters, and that's to the east. We can go back to these other ones. X1 is also meters to the east. Y1 is meters, but that one, since it's in a Y direction, it looks like it's going to the north. That's really important. That'll be especially important when we calculate this next number here. So the next number we got to find, of course, is our y2. That is our opposite side of this triangle. So opposite and hypotenuse will be sine. So we'll say sine of 10 equals y2 over 35. 35 is our hypotenuse here. Multiply 35 over, and we've got y2 equals 35 times sine 10. That's going to be 6.0777, we'll say. That'll just round again. So I'm keeping it 4 decimals for all these. This time around, though, I want you to notice y2, that's going in the south direction, right? That one's not going north. So that is why, oh, I forgot meters. That is why it's so important to include your direction, because north and south are opposites. One of them is going to have to act as a negative number here. Now, for my hint as to which one acts as a negative number, I usually just say whatever the smaller number is can act as negative, because the bigger one obviously is going to dominate that other one, right? So when we add all these together, and I'll do it now, just change pen color so it sticks out. When we add these together, we just need to be mindful of what direction things are going. So x1 and x2 are both going east. There's no ifs, ands, or buts about that. That means x3, which is our total amount of x all the way along here, x3 is just going to be the sum of those two numbers. So we'll say it's 9.6418 plus 34.4683. Let's see what that gets us here. Give me a second. 9.6418 plus 34.4683. There we go. That's going to be 44.1101, and that's meters to the east. That's all well and good. Now let's worry about our y's. Y3 is going to be this component over here. It's just the sum of y1 and y2. So y3 is going to equal our y1, which was 11.4907, and that was to the north. Let's take away the south y2, right? So we'll minus 6.0777 because that is going south. Let's see where this ends up. 11.4907 minus 6.0777 gives us 5.413 meters. And of course, our positive direction we chose was north. So we're all good there. Remember at the start of the question, I was like, oh, gee, I hope my diagram is kind of accurate here. I think it was. I think that was actually a pretty fair diagram. Could have been better, but it also could have been a lot worse, right? If my diagram had shown like the arrow ended up going south, that just means I screwed up my diagram. Trust your numbers better, right? Your numbers are more important than what your diagram is, especially if you didn't measure your diagram exactly. I just did mine freehand. You saw me do it. Anyway, Draw an arrow from your starting position to your final position. That's your resultant vector. That actually wasn't too bad. I've done worse than that. That's your resultant vector. We want to find the magnitude and the direction of that. So we want to find out not only how long that solid red line is, but also at what angle that comes up at, right? We know that we're going east and then north. So our answer will be north of east. We just need to have an angle number for that. So to box this off, just to get our final work done on this one, to solve for the length of that line, you just have to use Pythagoras because this is indeed a right triangle. So take x3, that's 44.1101, and square it, plus 5.413, and square that number. And that is going to equal our hypotenuse squared. I'll just call it c squared. Let's see where this gets us. Hold on, plus this and this, 44.1101 squared. Okay, and I'm not going to bother writing the big answer that comes. I'm just going to square root it. So if we just square root all of this all at once, right? Anyway, long story short, C is going to equal, and we can actually round this one to our sig digs. Shoot, it's just going to be 2 sig digs because we didn't add more on our direction there, and those do in fact count. That is going to be 44 meters. Yeah, 44 meters because I'd have to round down. I got 44.4, but 2 sig digs, it'll be 44 meters. Great, awesome. Okay, last thing we got to do here is we got to figure out what that angle is. Okay, now keep in mind, with this triangle, this red triangle that we've got here, Y3 acts as our opposite side, X3 acts as our adjacent side, and we know those sides. They're right here and right here, right? We got to use trigonometry on that. Opposite and adjacent, that's going to be tan, right? So we can say tan theta equals opposite, which is 5.413, over adjacent, which is 44.1101, and then use inverse tan on that. So take inverse tan of both sides, inverse tan of this whole fraction right here. I don't know what the answer is going to be. We'll find out in a second. As I'm typing this in, I'll just tell you, I bet it's going to be a pretty small angle because that does not look like a very big angle at all. Rounding to 2 sig digs, that's actually quite nice. It rounds right up to a nice number. Theta equals 7.0 degrees. Yeah, so a pretty slim angle, right? It's not really going too high. Let's polish this off by putting all this stuff together. It's going to be a final answer of 44 meters, and then square bracket, 7.0 degrees. And remember, we went east and then north with where our arrow is going from the starting point to the ending point, east, then north. So it would be north of east. It's always kind of backwards. Perfect. That would be your final answer there. It's a shame that we only had 2 sig digs. It kind of messed up that actual magnitude of the direction, but it is what it is. Follow your sig digs. And since you use those numbers in calculations, sig dig rules still apply. You have to use them. Anyway, we have one more question we're going to do today, and then I'll let you guys just have free independent practice time. I told you it was actually going to end up being kind of longer. I thought the video would be shorter than this, but that second question was long. Anyway, here's another real thinker. I don't think it's quite as bad as that last one. Suppose a boat wants to cross to the east side of a river perpendicular to its current. Okay, so you're going directly across a river. The river current has a velocity of 2.5 meters per second north. The boat motor pushes the boat at 12.0 meters per second. So that's like your actual quote unquote water speed if you're going in, right? The boat decides to sail at 12 degrees south of east in order to travel straight, right? So it's compensating for this river current pushing it north. So it's traveling a little bit to the south. How long would it take to sail across the river if the river is 50.0 meters wide? There's going to be a couple things that go on in this one. Pause the video here. You can jot the question down if you want. You don't have to because it is kind of bulky, but try it on your own or with a partner, and I'll go over it in a second. Okay, first things first, as always, let's draw ourselves a really quick picture here, right? So we're trying to cross to the east side of the river, so we're going from west to east. So if we'll say this is one riverbank and this is the other riverbank, we ultimately want to get from here to here. We want to go straight across, right? So what the boat is doing is it's going 12 degrees south of east. South of east means draw east first and then draw 12 degrees south of that. So that'll be like pointed this way-ish. That's a little bit exaggerated. I'll even clean up this line so it's a little bit more straight. Let's do what I can here. That's a little bit better. That's going to be 12 degrees south of east, and the river is flowing this way. So it's going to ultimately push it back up so it ends at this point. So just for clarification, this is going to be our start position, and this is going to be our end position. We're going to travel in a straight line across this river, right? Now, we know that angle was 12 degrees south of east. We also know that the river current is 2.5 meters per second. I'll just change color just so that can stick out a little bit better. 2.5 meters per second to the north is going to be this arrow pushing it up here, right along the riverbank on the east side. So that's 2.5. The 12 meters per second, which is the boat motor, is the way the boat is pointed. So your boat speed that you have, like from a motor, or if it was an airplane, like your engine speed, that's the direction you're pointing. We're pointing 12 degrees south of east. So that's going to be this right here, 12.0 meters per second. The question's asking how long would it take to sail across the river if the river is 50 meters wide? Don't get carried away here. This 2.5 is meters per second. This 12.0 is meters per second. You can't just go and say that this is 50 meters because that doesn't match up with your meters per second. What we need to do here is we need to find how fast they're going straight across the river. It's going to be probably a little less than 12 meters per second because they're boating into the stream, like against it. So it's going to slow them down a bit. But if we can find how fast they're actually going directly across the stream, we're going to be fine, because then we'll have a velocity, we have a distance to cover, and then we can find a time. Anyway, I'll stop rambling. I'll show you actually how to do this. We need to figure out how fast we're going, so we just got to use Pythagoras. 12 is our hypotenuse, so that's going to be the side on its own. So we're going to have question mark squared plus 2.5 squared equals 12 squared. Well, 2.5 squared, give me a second here. 2.5 squared is 6.25. So we have question mark squared plus 6.25 equals 12 squared, which is 144. Subtract that over, 144 minus 6.25, and we have question mark squared equals 137.75. Oops, don't need units. What am I doing here? Now I got to square root it. So our question mark, in other words, our speed that we're going to be traveling across this river here, is going to be 11 point, and I'm going to keep many decimals here, 11.7367 meters per second. That is the velocity that the boat is actually traveling across the river, going completely straight, just completely from west to east, completely straight east. Now, we know the river is 50 meters wide. If it is constantly going at this speed, we have something called uniform motion. And from earlier in this course, hopefully you remember, with uniform motion, when something is going at a constant speed, you can use the very simple formula, V equals distance over time. We know our velocity, that's the 11.7367. We know our distance, it's 50 meters. Time is what we're looking for because it was asking how long. Throw the numbers in. 11.7367 equals 50 over time. Multiply by time, that's 11.7. Ooh, getting carried away here, hold on. There's my eraser. There we go. 11.7367 times t equals 50 divided over. So t equals 50 divided by 11.7367. Long story short, to just 2 sig digs, both there, and actually this one wouldn't count because we never even use that number. So haha, but this one is just 2 sig digs. So 50 divided by 11.7367 gives us 4.3. Unfortunately, it has to round way up. 4.3 seconds. That's kind of weird. That's actually a lot less time than I was thinking. That's a pretty, that boat's clipping, in other words. Holy smokes, 4.3 seconds. That's actually kind of disappointing. It's like, wait a minute, you're only in the boat for 4.3 seconds? Okay, well, the math checks out, though. That's how it would work. And hopefully that one was hopefully a little bit better than that last one with the little football thing, right? Anyway, that's it for today. So for practice, you can use that navigation vector handout from last class, or even any of the previous ones. There's like 2 or 3 we've done since. I know it says an exit slip. That was from another time. You notice even those times don't even line up. Don't even worry about that. But just remember, you might want to have a look through sections 2.2 and 2.3 in the textbook. Feel free to borrow the ones behind the desk. Just don't take it out of the room unless you had signed it out with me before. Anyway, best of luck, guys. If you need any help, please reach out.